Hello and welcome to this video for the 2022 Level 1 Mechanics paper for NCA. So we're just going to get straight into it. So we're going to look at America's Cup boat. And below is a distance time graph for the America's Cup boat sailing across the Waitemata Harbor. So you want to describe the motion of the boat into four sections. We have section A, section B, section C, and section D. So for section A, we'll see that there's a curve in the graph. So as you can see here, we cover a small amount of distance at the start with respect to time, and we cover more distance with time as the time goes on, which indicates that we are accelerating. So we're increasing in speed in this section. So for section A, we're going to be accelerating. Looking at section B, we're looking at a straight line. So we cover a constant amount of distance over time. A constant distance over time indicates that we are traveling at a constant speed. And that is the same for section C. So for section C, we're also traveling at a constant speed. Since we're traveling at a constant amount of distance over time, that's seen by a straight line. And for section D, we see that we're covering no distance with respect to time. So in 20 seconds, we've covered no distance. So we're actually stationary at point D. So for section A, we are accelerating. Section B, we're doing a constant speed. Section C, we're also going at a constant speed. And for section D, we are stationary. We've stopped or stationary. And that's all we need to do. We just need to state the type of motion for each of those sections. And if you get all four correct, so 4 out of 4 is a merit grade. And if you can get 2 out of 4, that is an achieved grade for this question here. Perfect. Let's look at question BI. On the axis below, we're going to sketch a speed time graph for this journey. Section C has been done for you. So this axis has not been labeled, so we're going to find the speed at section C to know what scale the graph is at. So for section C, we're going to look at between 40 and 60 seconds, so this part here. And we've traveled a distance of 800 minus 300 meters. So distance traveled is equal to 800 minus 300, which is 500 meters. And we've traveled this in exactly 20 seconds. So the velocity is equal to the distance over the time. So that's 500 divided by 20. So that is equal to 25 meters per second. So that's 25 meters per second. So with respect to the graph, if we look here, so this is 25 meters per second. And so therefore, each one of these axes is equal to 5 meters per second. Okay, so each of these is 5, 10, 15, and 20. Okay, so let's look at the section A. So for section A, we are going to be accelerating. And for the purpose of NCA Level 1, we're just going to assume that we're accelerating at a constant rate. So the increase in velocity is constant. So we're going to assume that some constant increase in the velocity. And we increase in velocity to the same velocity as in section B. And in section B, our velocity is given by distance over time. So for section B, we have a distance over time, which is equal to a distance of 300 minus 100, which is 200, divided by the time, which is 20 seconds. So that is 10 meters per second. So therefore, in section B, we're traveling at 10 meters per second. So section B would be 10 meters per second for section B. And for section A, we're going to be assuming that we have a constant acceleration to 10 meters per second. So that will be our constant acceleration to 10 meters per second. And we just join the graphs here. And then for section for section D, we know that the boat is now stationary, so it has a speed of 0. So the speed at section D would be 0 meters per second. So that's what our graph should look like. So a constant acceleration for the first 20 seconds to 10 meters per second. A constant speed at 10 meters per second for 20 seconds. Then we have a constant speed at 25 meters per second for 20 seconds. And finally, we have a speed of 0 for the last 20 seconds. And this is an excellence level question. If you can label all 3 of these parts correct, that will be an excellence. So that's a 3 out of 3. For a merit, if you can get 2 out of the 3 sections correct, that is a merit. And for an achieved, if you can label 1 out of 3 of these correctly, that is a achieved grade. We want to calculate the speed of the boat in section B of the graph. We've actually already done this, okay, but we've already kind of done this in part 1 in order to draw a graph. So we know that for B, we know that distance over time will give us the velocity, the constant velocity. And the velocity is going to be equal to, we had 300 minus 100 over the time, which is 20 seconds. So this would be 200 over 20. So this is equal to 10 meters per second. And this is an achieved level question for a correct calculation of the constant speed in section B. Let's look at question C. On the diagram below, we want to draw and label arrows to show the size and the direction of the horizontal and vertical forces acting on the boat for section A and section B of the boat's journey. So if we recall, in section A, we had a constant acceleration up to 10 meters per second from initially we were stationary. So if the boat is accelerating, we know that the direction in which the boat is traveling in will have a higher force than the drag or the forces that are acting against the boat. So for the horizontal forces, we know there's a net force in the direction that the boat is traveling in. So assuming that the boat is traveling to the right, okay, we're going to make that assumption. So assume boat is traveling to the right. It's good to always state that, so just assume boat moving to right. So therefore, we're going to have some horizontal forces. This is going to be the acceleration, so we're going to say this is some thrusting force towards the direction it's traveling in. And obviously, since the boat is traveling in water, there's going to be some sort of drag force or some friction force due to the water. And that's going to be acting in the opposite direction of the thrust. So that's going to be some drag force in the opposite direction of the thrust, but we know that the boat is accelerating in the direction it's traveling in, so the thrusting force is going to be greater than the drag force in this case. In terms of the vertical forces acting on the boat, we have the weight force of the boat, which is acting downwards, and we also have the support force from the water, which is going to be holding the boat up. And we know that these must be equal in size, because if they weren't equal in size, we'd expect the boat to accelerate in the upwards and downwards direction. So either the boat is going to start floating upwards, or the boat is going to start sinking towards the bottom of the sea. And since we know that none of those things are happening, we know that the forces must be balanced in the vertical direction. So there's going to be some support force from the water, and there's going to be an equal-sized gravity force, so F weight of the boat, which is going to be acting in the downwards direction. For section B, we know that the boat is traveling at a constant speed, so there's no acceleration in any direction, which means that the boat is in equilibrium, so therefore there are no net forces acting on the boat. So in this case, the horizontal forces are completely balanced, and the vertical forces are also completely balanced. So we have a F thrust force, which is going to be forwards. And that's going to be equal in size to the drag force, which is going to be in the opposite direction. And similarly, again, the boat is not moving upwards or downwards. So we are going to have the weight force acting down, which is equal to the support force acting upwards. Okay, so in this case, that's all we need to do in terms of the labeling. So we draw and label arrows to show the size and the directions. That's all we need to do. This is an excellence level question. If you can name all forces drawn on the correct sides, that is an excellence grade. If you can make one correct diagram, so one correct diagram is a merit, and 2 correctly named forces would be an achieved grade. Okay, so for question D, we're going to compare and contrast the forces acting in section A with the forces acting in section B. We should consider both the horizontal and vertical forces, the size and the direction of these forces, and the motion of the boat in both sections, and the net force in both sections. So first thing what we can start off with is quickly saying why the vertical forces are the same in both situations. So for both A and B, we know that the support force is equal to the weight force acting downwards, since the boat is not accelerating upwards or downwards. So we know that for section A and B, the support force from the water is equal to the weight force acting downwards. And this is because the boat is not accelerating upwards or downwards. Since for neither A or B, the boat is accelerating downwards. So the forces in the vertical directions are balanced. So the forces in the vertical direction directions are balanced, so there's no net force in the vertical direction. So no net force in the cool. Now we can look at the horizontal forces. So in A, this boat is accelerating. So the thrust force in the direction it's traveling in is greater than the drag force. So in section A, the boat is accelerating in the horizontal direction. The boat is accelerating in the horizontal direction, so there is a net force in the horizontal direction. The thrusting force is greater than the drag force. So the boat accelerates in the direction of the net force. In section B, it is boats at a constant speed, so there's no net forces on the boat, so the thrust is equal to the drag. So it's traveling at a constant speed. So therefore, the thrust forces, the thrust and drag forces are the same. So I mean, when I say same, I mean equal but opposite direction. Yeah, and that's all we really need to say for this question. Okay, so the net force, we've considered the net forces, the motion of the boat, the size and direction of the forces, and both horizontal and vertical for sections A and B. This is an excellent level question. If you can link the net force horizontally to the velocity and the acceleration for section A, and we can link the balanced upwards and downwards forces so the boat is not accelerating in the vertical direction. Okay. So that's an excellence if you can get those points there. If you only link the net force in one section, that is a merit. And if you correctly name two vertical or horizontal forces, and if you say that balanced forces cause constant motion, that can be an achieved grade there. Okay, let's look at question 2. So question 2, we're going to be sandboarding at Cape Reinga. So a sand hill has a vertical height of 25 meters. Ariana and her sandboard have a mass of 55 kilograms. Explain the difference between mass and the weight of Ariana and her sandboard. So the mass is referring to the amount of matter stored in Ariana and the sandboard, while the weight is referring to the weight force acting on Ariana and her sandboard due to gravity. Okay, so the mass is the amount of matter in Ariana and the sandboard, but the weight refers to the downwards force, which is due to gravity. And notice that the gravitational field strength on Earth is about like 9.81 meters per second and per kilogram. But for in terms of the weight of Ariana and her sandboard can be different depending that she is in a different gravitational field strength. So for example, on Mars, we expect Ariana and her sandboard to have a smaller weight. However, the mass of Ariana and her sandboard is gonna be roughly constant, assuming that there's no loss or gain in mass. So mass is going to be amount of matter that's relatively constant. However, the weight of Ariana and her sandboard will depend on the gravitational field strength, which on Earth we know is 9.8, but on another planet, for example, it can be something different. So Ariana and her sandboard can have different weights. Okay, so for part B, so Ariana carries her sandboard to the top of a 25-meter hill in 120 seconds. Calculate the work done to climb the hill. So the work is just going to be the amount of force times the distance, okay? So in this case, in NCA level 1, we assume that G is 10. So with G equals to 10, we're going to have work is going to be equal to some force times distance. And in this case, Ariana needs to bring herself and her sandboard, which is going to have some weight force acting downwards, up a height of 25 meters, okay? So the force is going to be equal to the mass times the gravitational field strength, so that's going to be 10. So that's going to be 55 multiplied by 10, which is 550 newtons. And now the work done is going to be the amount of force, so that's 550 multiplied by the distance traveled, the vertical distance traveled, which is 25 meters. And that is going to be equal to 13,750 joules. So it's going to be 13,750 joules of work done to climb the hill. Calculate the power she uses to climb the hill. So the power is going to be the amount of work done over the amount of time it took for that work to be done. So in this case, we took a work of 13,750 and we took a total time of 2 minutes or 120 seconds. So the power is going to be equal to 13,750 divided by 120, which is 114.58 watts. So this would be an average work output of 114.58 joules per second. So on average, Ariana did 114.58 joules per second of work in order to reach the top of the hill within 120 seconds. Let's look at part III, part 3. Explain how she could lower the power output required to climb the top of the hill. So since the top of the hill stays a constant height of 25 meters above where she starts, we know that the height or the distance is not going to change. We also know that Ariana and her skateboard is going to have the same mass and therefore it's going to have the same weight force. So therefore the force is not going to change as well. So how we're going to lower the power output is we're going to be changing the time. So we're going to stretch the same amount of work done over a longer period of time. So on average, each second, we're going to be doing less work and therefore the power output will be reduced. Okay, so to reduce the power output, we will, in other words, Ariana will, that's probably better. So Ariana should climb the hill in a longer period of time. The amount of total work done is the same. The amount of total work done is the same, stretched over a longer period of time. So in this case, we can stretch over a longer period of time, so less work per second. So less work per second, and hence a reduced power output. Okay, so in this case the work stays the same, but we do less work per second since we're doing it over a longer period of time, so we have a lower power output. Okay. So for this particular question, if you can do calculations correct, so both I and II are correct, and we can say that the power can be reduced by keeping the work the same and increasing the time taken. So just saying that we increase the time taken and the same number of work, and that will be an excellent double grade. For a merit, you can get both calculations are calculated correctly, and we explain how power could be reduced by increasing the time taken. So you're not linking it to the same amount of work. So that will be a merit. And to get an achieved, if you can do one correct calculation, that would be an achieved. All right, for part C, we know Ariana rides a sandboard from the top of the 25-meter hill to the bottom. Calculate the gravitational potential energy of Ariana and her sandboard at the top of the hill. In terms of the gravitational potential energy, we actually already calculated this, since the gravitational potential energy is going to be equal to the amount of work done that Ariana does in order to reach the top of the hill. So Ariana needs to do work against the gravitational field strength in order to reach a height of 25 meters, which is on the top of the hill. And therefore, it's going to gain some amount of gravitational potential energy. And the gravitational potential energy gained is going to be equal to that work done by Ariana and her sandboard. And of course, this is assuming that we have no losses to heat. So in reality, Ariana might have some sweating. There might be some energy losses due to friction. So in reality, they're not going to be exactly equal. However, in the ideal case, we're going to assume that the work done or the amount of work output of Ariana is going to be equal to the amount of gravitational potential energy that she gains. Alternatively, we can just use the formula EP equals to mgh in order to calculate the gravitational potential energy, which is going to be 55 times 10 times 25, which is going to be the same answer of 13,050 joules. However, we also know that it's just the same amount of work done. So since she loses or she does 13,750 joules of work, so she gains 13,750 joules of gravitational potential energy. So work done, so this is alternatively work done. Work done is equal to gravitational potential energy gained, so EP gained, which is equal to 13,750 joules. For II, we know her speed at the bottom of the hill is 12 meters per second. Calculate the kinetic energy of Ariana and her sandboard at the bottom of the hill. So we know that the kinetic energy is given by half the mass times the velocity squared. So this is 1/2 of 55 multiplied by 12 to the power of 2. So this will be equal to 3,960 joules. Explain the differences between her gravitational potential energy at the top of the hill and her kinetic energy at the bottom of the hill. So at the top of the hill, we had a EP of 13,750 joules. However, the EK at the bottom we calculated was 3,960 joules. So as you can see, we've lost quite a lot of energy, and this would be due to losses of energy due to heat and friction. And this would possibly be the friction between the board and the sand, or it could be the friction between Ariana and the air particles. So this could also be some friction there that will cause some heat losses. And alternatively, there can also be some losses to sound energy due to the sound which could be occurring when the board rubs against the sand. So that could also be another source of loss of energy. So we know that EP is converted into EK when Ariana slides down the hill. However, some of that energy is going to be lost to friction and heat. some energy lost due to friction, heat, sound between the board and the sand. And Ariana and the air particles, perhaps. So Ariana and the air particles. Which is why the EK at the bottom of the hill is less than the EP at the top. And that's all we need for this question. Okay, so for this question, it's got a 3-part question. If we can correctly calculate the workings for part I and II, and we also state that not all of the EP is converted into EK, and some of them is lost to heat and sound due to friction of the board against the sand. So therefore, that will be an excellence level grade. Okay, so if you can get all 3 of these parts correctly, that's an excellence. In terms of getting a merit, if you can do one correct calculation and states that not all EP is converted into EK, that is a merit. And if you can get an achieved, just attempting the first calculation is an achieved. And if you state that some energy is lost, that can be an achieved grade there as well. Let's look at question 3, steep hills. So for question A, we want to identify what each of the letters mean in the formula. So including the units used. Okay, so for the letter P, that's going to be the pressure. So that's going to be the pressure, which is measured in pascals. Pressure, which is going to be measured in pascals. And the pascals, which is going to be, we can use pascals, or alternatively, we can say that this will be some newtons, some force, which is measured in newtons, over area, which is meters squared. So it can also be newtons per meter squared. F is still going to be the force, and that's going to be measured in newtons. And the area, which is going to be some meters squared. All right, and this is a merit level question. If you can do everything correctly, to get an achieved, if you can define 2 terms, you'll get an achieved. So 2 out of 3 is an achieved. Question B, so cars need effective brakes when driving down a hill. A brake system in a car uses 2 pistons, a small piston with a small area and a large piston with a large area. Braking causes a small piston to move with a force of 20 newtons. The piston has an area of 0.008 meters squared. Show that the pressure is 2,500 pascals. So we know that the pressure is given by the force over some area. And that's going to be some force of 20 newtons divided by 0.008 meters squared. And that's going to give us a value of 2,500 pascals. All right, so question II. The pressure is the same in all parts of the braking system. The large piston has an area of 0.04 meters squared. Calculate the force applied by the large piston when braking occurs. So we know that the pressure remains the same, however the area is different. So again, it's just going to be pressure equals to some force over area. So the pressure stays the same at 2,500, and it's going to be some force we don't know over the new area, which is 0.04. So now the force will be equal to 2,500 multiplied by 0.04, which is going to be equal to 100 newtons. And if you can do both of these parts correctly, that's an excellence level grade for both correct calculation for both parts. To get a merit grade, if you can get the correct answer without the units are very important. So if you miss out the units, you'll get a merit. And a correct rearranged formula with incorrect values. So if you have the correct formula but get the incorrect value somehow, you'll get a merit. Let's look at question C. A car is moving along a flat road at a speed of 20 meters per second. it comes to a stop 4 seconds later. So we want to calculate the acceleration of the car over the 4 seconds. So in this case, the total amount of time it took for the car to come to a stop is 4 seconds. And it was moving at a speed of 20 meters per second. And we're going to assume a constant acceleration, or a constant deceleration in this case. So assume constant acceleration, so A. So the acceleration is going to be the change in velocity over the change in time, which is going to be negative 20, which is going to be losing 20 meters per second of speed in 4 seconds. So this will be a acceleration of negative 5 meters per second squared. So this is negative 5, so this indicates that this is a deceleration. So this could either be an acceleration of negative 5, or it could be a deceleration of positive 5. So either one of those is okay. So acceleration is negative 5 meters per second squared. For part II, the car and the driver has a mass of 1,000 kg together. We want to calculate the force required to stop the car. So we know that F is going to be equal to ma. So F is going to be equal to the acceleration, which is 5 multiplied by 1,000, which is going to be 5,000 newtons. So there's going to be a net force of 5,000 newtons acting on the car. So if we have the car here, that's going to be some force here, and there could be some drag forces acting in this direction. This will be the FD, and there might be an some FT. So FD minus FT is going to be equal to 5,000 newtons. So the net force on the car is acting with a magnitude of 5,000 newtons in the direction it's slowing down in. So that will be the net force required to stop the car. And we want to explain the direction of the force. So this will be in the opposite direction that the car is traveling in. So this force, or this net force of 5,000, this net force of 5,000 newtons is in the opposite direction of the direction of travel of the car. And this is because the car is slowing to a stop. Okay, and that's all we need for this question. Okay, so for an excellence level grade, if you can get 2 correct calculations and you're saying the direction is in the opposite direction that the car is moving in, that is an excellence level question. Okay, so that will be an excellence if you can get up to this step. To get a merit level grade, if you can have 2 correct calculations, so 2 correct calculations is a merit. And you can get a merit by mentioning the direction of the force to cause the car to slow down. So if you say that the direction is in the opposite direction that causes the car to slow down, that's a merit. To get an achieved, if you just attempt the first and second questions, you'll get an achieved. And if you mention the direction of the force, you'll also get an achieved grade there. And that's it for this paper. That's all for the NCAA Level 1 Mechanics. I hope you enjoyed the video, and I hope to see you all in the next one.